Alright, welcome back. We are doing question 10 now. Right, question 10. A flat circular coil is connected in series with a battery of EMF 6.0 volts and internal resistance. Oh, that means that we have to consider both Emag and DC together. Right? It's connected in this figure shown, and they give you a flat circular coil, and they tell you, right, nicely, very nicely, they tell you the value of the current. Right, show that the resistance of the coil is this value, so let's set it up. Right, we know that the EMF equals to I times R total. EMF here is 6.0 volts as given by the battery over here. Current is just 1.2 amperes. It's given. Oops, we didn't need to put in that amperes. Total resistance. Well, there's the resistance of the internal resistance of 0.10, and there's the resistance of the coil. Are there any other resistance? Nope, does not look like it. So 6.0 divided by 1.2, the answer is 5. Equals to 0.1 plus resistance of coil. From here on, it's a simple subtraction. Resistance of coil will be 4.9. Done. Moving on, what else did they ask? Oh, let's write down some of the clues that we have here. The diameter of the coil is 22 cm, so I believe that will help us later. Right, let's move on. Part 2. The flat coil has a diameter of 22 cm. It is made of copper wire of diameter O. So this is the diameter of the coil. And if you look at a small part of the wire, you zoom in, this wire has a diameter of 0.60 mm. Okay, so do not confuse the two diameters, they are not the same. It has a resistivity rho of 1.7 times 10 power minus 8 ohm meter. Right, determine the number of turns on the coil. Right, so here we know that the initial resistance is this value. We have rho, right? We have this diameter here, which tells us the cross-sectional area. We have the diameter of the coil, which suggests for us that we may be able to find the L. So it all points towards, all the clues points towards using this equation. R equals to rho L over 8, right? So essentially, we are looking at the clues given to us and we are making some deductions. Right, how does that help us find the number of coils, number of turns? Well, if you can find the length of the wire, find the length of the wire divided by the circumference, you can find the number of turns, right? So let's try and find L. For me, I will find L first. I break it up. L equals to A R over rho. Area is pi d over 2 square, where d is this, so it would be 0.60 times 10 to the power minus 3 divided by 2 whole thing square, so pi r square. Always check for your square, very common mistake. Resistance is 4.9, resistivity is 1.7 times 10 to the power minus 8. So you'll get a certain length L of the wire. How does that relate to the number of turns, as I mentioned? Let me just scroll this down to give myself more space. Oops, too much. So, L divided by 2 pi R, or rather pi D, 0.22 meters. Right. Should give you the number of turns. So all we have to do is to take this divided by pi and divided by 0.22. Right, let's see if that's what we have in the solution. So here, yes, it looks more or less the same. Right? Scroll down. Oops. You see that the 4.9 here is similar to the 4.9 over here. Wait, circle it. The 0.6 is, oh wait, okay, so here they use this, right? They brought the, and this is down here, 0.2, yep, they squared the 4, right? They brought this down to the bottom, right, to make appear this 4, 1.7 is there, 0.2 is there. So you plug in all the numbers, you should get 118. That shouldn't be too much of an issue. Right, next. Two flat coils, each similar to the one in A, are fixed so that their planes are parallel and separated by a constant distance as shown below. Right, so this is what it's like. So depending on the coil direction of current, imagine they're the same, there should be a B field induced at the middle of the two coils, right, through the middle axis of the two coils. So to be more accurate, not just in the middle between them, but through the axis of the two coils here, through here, and right. So the current in both coils is 1.2 amperes as before. The magnetic flux resistance density B in the region is given by this value. Yeah, we can actually calculate this if we want to, but since they have already given it to us, we'll just take it as it is. Where n is number of turns for each coil, so we already calculate n to be 118 over here. Right, n equals 118. You can sub all of these values in. Use your answers in A part 2 to show that the magnetic flux density is approximately this value. Oh, isn't this just a sub in question? So we can sub in the values of mu naught. Sub in the values of mu naught. Sub in the value of n to be 118. Current is 1.2. R is 0.11. Right, because R is the radius of the coil. So we sub in everything, we get answers of 1.2 millitesla shown. Okay. I guess this is still pretty early question. They don't want to make it too difficult. The space between the two coils is a vacuum. An electron is accelerated from rest in the vacuum through a potential difference of 250 volts. Right, so the energy of the electron, right, must have is of the value U equals to Q delta V, right? It's accelerated from rest, right? So the initial value, if this should be change in energy is Q delta V, but since the initial energy is 0, you can just write Q equals to Q delta V. We know that this is 250 EV, right? Not that difficult. It travels at right angles to the magnetic field produced by the two coils. Calculate for electron the magnitude of its momentum. Okay, so here we have a little bit of kinematics involved. So this energy is half mv squared, so half mv squared equals to U. We can also rewrite this as momentum, p squared over 2m, right? In case you don't know, if I multiply by m and the numerator, I get m squared, v squared over 2m. So mv or thing square is P square 2m, right? This is how you find the, so we know that P square over 2m, alright, is 250 electron volts, so that's essentially just 1.6. Converting it to joules times 10 to the power minus 19 times 250 volts. That's the amount of energy in joules that we have. So all we have to do is to rearrange. So P equals to 2m. The charge of electron is given by E. Oh, let's use a different color. It's not that looks like a diva. So this is just E. This is just V, which is why you have in the equation E and V over here holding square rooted, as shown here. Okay. Once you have that, once you can get this equation, the rest is just a substitution. Purely math. I'll leave it up to you, right, to get this value of 8.54 10 to the power 24 kg meter S minus 1. Next, we are asked to find the radius of its orbit in the magnetic field. Right? This is more in the realm of Emag. Right? We have, imagine that the two coils have, right, the B field points this way. Imagine the electron is coming out this way. So if you're now looking from this direction, what do you see? Right? You'll see B field pointing in to the pitch. We have the velocity coming out. So velocity is coming out this way. So using your left hand rule, an electron moving up is as if the current is down. So field is into the page, current is down, page of force is to the right. So you will force to the right, which means you do circular motion like this within the field. Okay. Of course, I'm assuming that the magnetic field is turned on when the electron reaches this point at a certain V. Right? If the electron were to come in from the outer edge, the likelihood is that it will do a semicircle and it will exit like this, right? But that wouldn't be so interesting, would it? So let's leave it like that. Okay, so the radius of its orbit. So here, FC, right, this is the time we are doing this today. So centripetal, so mv squared over r equals to dqv. V and v squared goes away. R equals to mv over bq. Right, so you have to sub in the mass of the electron. 9.11 10 to the power minus 31. The velocity. Oh wait, you don't have to sub in that because mv is actually just the momentum. So let me rewrite this as the momentum over bq. And this whole thing is 8.54 times 10 to the power minus 24 as you have found in the previous part. The B field strength is 1.2 times 10 to the power minus 3 as you have found earlier. The charge is 1.6 times 10 to the power negative 19. Done. Sub in, find the value, not difficult at all. Right? Next, the field is now rotated. The initial direction of the electron is now at an angle with direction of uniform. Okay, so by considering the components of velocity at the right angles, describe qualitatively, right? You are not given a value of the angle, so you can't do it quantitatively. So do it qualitatively, the motion electron in the magnetic field. Well, this is pretty much a helix problem. However, because the direction of motion, this is where it gets really tricky, because it's not already inside when it happened. It cannot do the helix as we know it, right? Because it's already So here, what will happen is that you will do half a helical turn, and it should go up. Okay, it should. That's what it should do. But let's see what's suggested by the solution. Right. Let's see if that's true. Oops. Is it not allowing to move down? So the velocity of the electron is a component perpendicular to the B field and a component parallel to the B field, right? That's what we have done in the previous question. The perpendicular component causes circular motion, yes, and the parallel component causes move along the electric field. Yep. So it does a helical path, but it's actually half a helical path before it exits. Right? So it's still a helical path. Yep. And that's that. If you have any questions, please find me at the next lesson where we meet face to face. Thank you very much.